First of all, I would like to thank the organizers for the opportunity to present my work here. This is a joint work with Muriel and Ruiz, and as the title indicates, in this work I will present a geometric approach to finding traveling wave solutions of the generalized Korteweg-de Vries equation, or gKdV equation. The KdV equation is a nonlinear partial differential equation that describes the evolution of shallow water waves. It is a third-order equation that incorporates both linear and nonlinear effects, making it a fundamental model in fluid dynamics and soliton theory. It is a key example of an integral system which was derived by Korteweg and de Vries in 1895, when trying to mathematically describe the empirical phenomenon of solitary waves in shallow water. The equation has since become a cornerstone of mathematical physics. On the other hand, the generalized KdV or gKdV equation is a more general form of the KdV equation where the nonlinearity is represented by a variable function a of u instead of the fixed coefficient 6u. This allows for a wider range of physical phenomena to be modeled. In particular, we will be concerned with the traveling wave solutions of the gKdV equation, the solution that look like a wave moving at a constant speed. For this purpose, we apply the traveling wave ansatz, which is this transformation here, and in this way we reduce our original PDE to this third-order ordinary differential equation. In order to solve this ODE, we will use our geometric approach, which is based on the theory of cinf-structures. This method is rooted in differential geometry and allows us to systematically integrate the ODE by transforming it into a sequence of Pfaffian equations. As a first step, we substitute the target ODE with the corresponding distribution, the associated vector field set, and the distribution generated by set. That is, we translate our ODE into a vector field in the corresponding jet space. For our purposes, it's nothing but R4, in such a way that the integral manifolds, or better said, the integral curves of this vector field, of this distribution, have the form set f prime f second, where f is a solution of the ODE. So our goal would be to find an explicit parametrization of these integral curves, which is the same as finding the solutions of the ODE. The notion of cinf-structure, which is a generalization of solvable structure, is the key notion here in this approach. It is a collection of vector fields x1, x2 until xn in such a way that all the distributions appearing here when we add these vector fields are involutive. Remember that involutive means that the Lie bracket of any two vector fields in the collection is again inside the collection, and that Frobenius theorem, of course, states that involutivity implies the existence of integral manifolds. So, to recap, we have this vector field in R4 encoding the ODE we want to solve, and a cinf-structure would be something like this: a sequence of vector fields giving rise to a sequence of involutive distributions in such a way that they are the first one is very thin, it's only rank 1, and we have thicker and thicker distributions until the end that we recover R4. Okay, all of them has integral manifolds. The integral manifolds of this one, integral curves are our goal, and the last one as integral manifold, which is the complete, the total space R4. Observe that what we are achieved with this with as infinity structure is a kind of organization or filtration of the space R4 into a sequence of distributions, starting with this pink distribution here, this foliation here, and ending with the complete space R4. Okay, once we'll see how we can obtain a infinity structure, but once this infinity structure is found, the process to be followed consists of the following steps. We consider the standard volume form in R4, this capital omega here, and we define the one-fourth omega 1, omega 2, omega 3 by contraction. The one-fourth omega 3 is always Frobenius integral, and we can find a first integral I3 by solving this linear homogeneous partial differential system. So once we have a solution, we consider the level sets I3 equals C3 by fixing a particular value C3, and we find a parameterization iota 3. Okay. With this parameterization, we can go inside this particular level set. And how do we go inside? Well, we restrict our one-fourth omega 1, omega 2, and omega 3. Omega 3 is 0 when restricted to this, because this is the definition of this level set. And we are now inside where we have this another picture here where we have one level less of the foliation. So we repeat the process with the new omega 2 here, which is now a completely integral Fabian equation. At the end, the composition of the local parameterizations is a local parameterization of the integral curves of set. And this way, we're finding a parametric expression for the solution of the OD, for the prolongation of the solution. Okay, prolongation in the jet space. Indeed, once we have this parametric expression, if it is of the form f set f prime f second, we have the solution of the ODE, and anyway, at least the last expression I1 equals C1 is an implicit expression for the solution. So, coming back to our original problem, we have the gKdV equation, we have the ODE for the traveling waves, and we have the associated vector field set with this, which is this vector field here. Our next goal is to find a infinity structure for this vector field, for the distribution generated by this vector field. Fortunately, the vector field partial set is a Lie symmetry, so in this case, this distribution is involutive, and partial set is chosen as the first vector field for our infinity structure. Then we need the second vector field, and we propose this vector field following this ansatz, where eta is to be determined. In many samples in our research, we have found that this ansatz works very well. Indeed, we have proven that we can always find a vector field of this form, but this is still a work in progress. We impose the involutivity condition for the distribution, generated by set x1 and x2, and this condition result in this system of partial differential equations for eta, and it is not hard to find a particular solution as this one that you can see here. Since we are working in R4, that is, we are in a total dimension 4, we can choose any vector field that is linearly independent of the previous one to complete this infinity structure. Since these 4 vector fields will be trivially involutive. And so we choose, for example, a partial y2, and we have our decided infinity structure. We have the vector field set encoding the ODE and these 3 vector fields, which by construction are as infinity structure. Okay, to follow along with the method, we first write down the one forms, and we focus on the last one, omega 3, which is the first Pfaffian equation we must solve. We solve omega 3 equals 0 and we obtain this solution, which is the first integral of our ODE. Observe that the explicit expression for h1 will depend on the choice of the function a. Okay, it's here stated. And then we focus on the level sets by taking I3 equals C3. We take a particular value C3. We find a parametrization of this level set. With this level set is now a three-dimensional manifold. Recall that we can imagine something like this at this point. And now we restrict the one forms to this level set. Of course, the restriction of omega 3 is 0, and we are left with the other 2 one forms. And now we focus on the one form omega 2, which gives rise to the second Pfaffian equation we must solve. A solution to this Pfaffian equation is this function here, and we focus as before in the corresponding level sets. Now I2 equals C2. We find again a parametrization for this new level set. Now it is 2-dimensional, only z and y, and it lets us go deeper inside the structure of foliations, this kind of flag of foliations. We restrict to this leaf here, this 2-dimensional leaf. Now omega 3 and omega 2 equals 0, and we'll finally tackle the last Pfaffian equation, which is this one here. A solution is given by this expression you can see here, and therefore all the solutions of the ODE are given by this 3-parameter family of functions. Okay, it's an implicit expression for a 3-parameter family. But these are the solution of the ODE, not solution of the original gKdV equation. So we must undo the Charlene wave transformation, and then we obtain the solution of the gKdV in terms of the function f, which is the inverse of h3. Recall that the functions h1, h2, and h3 and f depend on the function a. So we are now going to take particular cases of the a function to obtain the explicit solution, the closed form solution for the gKdV equation. First, we consider this choice here, a equals 6u, and this is, we recover the original KdV equation, and we obtain these 2-parameter families of solution, which are well known. Observe that in the process we have had to take C2 equals C3 equals 0 to be able to find the explicit expression of the function h1, h2, or h3, or even for the parameterization. Sometimes we have to take particular values for the parameters. Now we consider this other choice, u squared for the function a, and with this other choice we have the so-called modified KdV equation. Our technique lets us obtain these two parameter family of solutions. Again, we have only the parameter c for the wave speed and c1. We can also consider a equals to u to the n over n, and this PD was originally called generalized KdV at the beginning, and we have this as result. We have these two parameter families of solutions, depending on C is positive or negative. And finally, if we consider, for example, A equals to alpha square root of u plus beta u, we obtain the so-called scalar KdV equation. This infinity structure based approach let us obtain, in this case, these two families of solutions which depend again on C and C1. So to summarize, we started with the goal of finding traveling wave solutions of the gKdV equation. We have presented a geometric method which uses the notion of infinity structure, which is a generalization of solvable structure, and we have shown how it can be used to integrate the ODE deriving from this for the traveling wave solutions of this PDE. Recall that generally idea is that we have a kind of flag of relation that let us to be restricting one dimension less and one dimension less till the end, and as a result we have a unified and general method to derive explicit solutions for a broad family of KdV type equation, okay, of this general form here. And that's all. Here you can find the bibliography. Thanks for your attention.